Okay, so we're working now in section 12.3, and we're talking about computing double integrals over general regions. And you had basically learned from sections 12.1 and 12.2 that a double integral can be interpreted as the volume underneath a surface function over a region D in the XY plane. And in section 12.2, the volumes were for rectangular regions in the XY plane. And in section 12.3, the volumes are now going to be over general regions in the XY plane. So the process of computing a double integral, you're all good at math, and so you know how to integrate. You have experience doing integrals, so it's really a process. Once you compute just to compute a double integral, all right. But where students have difficulty in multivariable calculus is a problem like this, where you need to compute the volume of something. Because in order to compute the volume of this particular volume, okay, the volume of this solid, whatever it looks like, you need to come up with a double integral. And that's where students run into difficulty. It's not so much computing the double integral, it's coming up with the double integral. And so I wanted to do this problem with you. It's from the book, but I'm going to add a lot more detail, or more detail, I should say, to the solution. All right, so let me give you a moment to copy it down. All right. All right, so we have to set up an appropriate double integral so that we can find the exact volume of this particular solid. So how would you, intuitively, how would you begin this problem? How would you begin it? What do you think? Okay, that's right, Robin. That's absolutely right. We need to draw a picture of this. Okay, and volume problems can get to draw the pictures. They can get difficult. Okay, but I'm going to try to keep your homework problems. I mean, they can get very, very difficult. Okay, but I'm going to try to keep your homework problems. I have to like reasonable, but there has to be, it's going to take some thinking, but I think they're going to be reasonable, what I'm giving you in terms of volume problems. So, okay, let's think before we draw a picture, let's think a little bit about what we got here. So, okay, oh, the plane z equals 0. The plane z equals 0. What's that plane? Is there another way of saying that plane? Can you describe the plane z equals 0? That's right, Eric. That is the x, and Robin. That's right. It's the xy plane. Okay. So this solid is bounded below by the xy plane. All right, no problem. Let's look at this plane here, x equals 0. Now, how can we describe the plane x equals 0? How would we describe that plane? That's correct. That's right, Eric. That's the YZ plane. Because in the YZ plane, all the points in the YZ plane have x coordinates of 0. Okay, so, we're just trying to, okay, now let's think even further here. Let's think even further. Are there any questions so far? Okay, good. I know nobody's doing the homework because I deactivated it. I like doing that because I want to make sure everybody's paying attention to the lecture. All right. How many might be tempted to do the homework a little bit if I didn't do that? I don't know. Sometimes I'll have a student says, "Oh yes, Dr. Duty," but you can be honest. But all right. So oh man, what's this? Now this plane here, x equals 2y. So if x equals 2y, that's equivalent to y equals x over 2 as well. Is this plane y equals x over 2 or x equals 2y? Would that be a horizontal plane or a vertical plane? If you had to choose, okay, Eric thinks vertical. Let's see. Well, let me ask you this, and Robin thinks vertical. When the plane, and Diodath thinks vertical, when the plane passes through this vertical plane, where does it cut the XY plane? How would you describe how this vertical plane here cuts the XY plane? What does the cut look like? Can you give me an equation for what the cut looks like? A plane would cut, this vertical plane would cut the horizontal plane along a line. What would the equation of that line be? Two planes intersect in a line. That's exactly right, Eric. X equals 2y. It would have to, right? It would have to, because x equals 2y always. So I'm trying to kind of give you just an intuitive feel for this, because I know the volume problems are difficult for students, but we have to cover them, and you have to be able to do them because it's important for your geometrical thinking, three-dimensional thinking. Are there any questions so far? All right, well, let's think about what we got here. We got a solid here. We're trying to find the volume of a solid. The solid is bounded below by the plane z equals 0. It's bounded in the back by the plane x equals 0. It's bounded on a side by x equals 2y. And then we finally have this plane here. So a solid needs to be bounded on this for a finite solid with volume. The side needs to be the volume needs to be bounded on the sides. The volume needs to be somehow bounded on its sides. The volume needs to be bounded below, and the volume also needs to be bounded. There's a word I'm looking for. Volume needs to be bounded on the sides, below, and above. Good. Well, here's the plane, x plus y, x plus 2y plus c equals 2. That plane is, it's not a horizontal plane, it's not a vertical plane, it's a plane at an angle, right? And that's going to be the plane that bounds it above. So this is going to be how we get our tetrahedron. So I'm going to go to the next page, and I have a lot written down there to help you on the solution. But are there any questions before we move to the next page? All right, Christopher's good. All right, let's go to the next page. Okay, remember, you can double click on the screen if you want to make the picture a little bigger. Well, maybe not, but I wrote it fairly big. I mean, it's good enough. So, okay, let's see what's going on here. First, let's talk about the picture. So, here's my picture here. Let me give you a moment to copy down the picture, okay? And then I'm going to talk about it in a few minutes. So I'm going to give you a few moments to copy the picture down, and then I'll talk about it. We'll do this kind of piece by piece. Okay, so, all right. So I rewrote the plane. As z. Hold on. I rewrote the plane as z equals 2 minus x minus 2y. So when z is a function of x and y, you get a surface. So I write the plane that way. And okay, well, how am I getting these intercepts? All right, well, on the z-axis, this plane would intersect the z-axis at 0, 0, 2, because when x is 0 and y is 0, z equals 2. The plane would intersect the y-axis at 0, 1, 0, because when x is 0 and y is 0, substitute that in the equation of the plane, and you'll get you'll hold on here, one moment. Yeah, you'll see that y would have to equal 1. All right. Now, okay, I got my plane below here, and my that's the plane z equals 0, and then in the back here I got the plane x equals 0. That's the yz plane. So this tetrahedron region or solid is bounded below by the xy plane and in the back by the yz plane. Okay, now on the side we have the plane x equals 2y. Okay, and what I did was there's an x here, class, by the way. There's an x there. This is the x-axis. In our in the xy plane, this vertical plane x equals 2y, or you could think of it as y equals x over 2. That's going to cross the I want to say it's the right way. That's going to cut the xy plane, the vertical plane y equals 1/2 x, or x equals 2y, is going to intersect the xy plane along the line y equals x over 2, and that's what I drew right here, y equals x over 2. So you see, then that helps me then, like, draw this part. Now, what is the intersection of the plane x equals 2y, or I'm going to call it, if you don't mind, y equals x over 2. What is the intersection of the plane y equals x over 2 and the plane z equals 2 minus x minus 2y? Okay, well, they meet at this point here. I want to get the coordinate right here of this point. So I note here, in this note here, that, well, there are two notes here. There are two notes, actually. Let's talk about both of them. When the plane z equals 2 minus x minus 2y intersects the plane z equals 0, then, well, both equations have to be true, so we substitute 0 in for z, and we solve and get y equals, well, hold on, no. That is true what I'm saying, but let me focus on this plane right here and this coordinate, because that's what I was talking about. How do we get this coordinate 1/2, 0? It has to do with the second comment. When that plane z equals 2 minus x minus 2y, when it intersects the plane x equals 2y at z equals 0, then this must be true. Z is equal to 0, okay, and x equals 2y. So I substitute that into the equation of the plane right here. And so you'll get then that for y equals 2 or y equals 1/2. And if y equals 1/2, by virtue of the fact that x equals 2y, or y equals 1/2 x, you'll get that x equals 1. And so that's how I get this coordinate here, okay, which we're going to need to use. Or, well, let's just, I like to kind of have things labeled, and, I like to kind of feel we do need to actually use that point. Now, So I've justified this one line here in the XY plane. And what's going on here with this other line that I've drawn in the XY plane? What's going on there? Well, when our plane intersects the plane z equals 0, okay, then, well, both equations have to be true. And so 0 would equal 2 minus x minus 2y, right? And so we'll get the equation y equals 1 minus a half x. Okay, so our surface intersects the xy plane along the line y equals 1 minus a half x. And based on that, then, I'm able to identify my region D, okay, in the xy plane. So this volume bounded above and on below and on the sides, that volume is up above the region D, and that region D, which is right here, right? I took the region D and I redrew it here. That region D is this triangle with the sides appropriately labeled. So this is, so, you know, now we're basically, I think we've, well, first of all, are there any questions at all? I know this takes time to absorb. I absolutely do. Do you have any questions at all? Absolutely, Christopher. You're going to need practice with this on the homework. Absolutely. Absolutely. And that's why doing the homework is so important. So you can see based on the picture here, and you know this point is the origin. This is the origin, obviously. You can see based on the picture, if I take this triangle here and draw it in 2 dimensions, this is what we're going to have. And these are the, you know, the corners are appropriately labeled. And the boundary lines are the boundary lines, y equals 1 minus a half of x, and y equals a half of x are the same boundaries that you see in you know, in the diagram here, the same boundary equations. All right. Are there any questions so far before we get, now I'm going to talk about how we get the volume, but are there any questions so far? You have to let me know if there's anything you're uncomfortable with. Chances are 2 other people are uncomfortable too, so feel free to speak up. All right, well, so now this, let me go ahead now and, well, no. Okay, so, well, I'll do this. All right, so now we have this region D. Okay, we have this region D here. And we're going to treat region D as a type 1 region. I'm actually going to do it both ways. But if we treat the region D, okay, as a type 1 region, that means your boundary functions are above and below. And traditionally, we draw a line segment with an arrow, just like I have that right there. So now the volume is represented with a double integral, whose integrand is the surface that's above the volume, and that should be not hard. That should be intuitive based on section 12.1, those problems where you had to approximate the volume. The question is now, what are the boundaries? Well, if I treat the region as a type 1 region, then I'm integrating with respect to y first. So that means the y limits are going to be my top and bottom functions for that bound the region D. And that's going to be 1 minus a half x and a half x. And then the limits for with respect to x, well, if we go to the picture, the limits with respect to x are going to be from 0 to 1, right? That coordinate there has x equals 0. This coordinate here is x equals 1. Are there any questions on how I'm getting the limits? See, once you get here, if you get this right, you're halfway home. You know, you're halfway there. And you want to try to get it right, because you don't want to go through calculating a double integral when your limits are incorrect, and then you get an incorrect answer. You know, so you want to take great care. And it takes time. It takes time. And practice. All right, well now, let's suppose that you treated region D as a type 2 region. Type 2 region would be, okay, let me just draw it here, region D. Type 2 region would be when you're using boundary functions that are on the left and the right. The left and the right. But in this case, if you're going to treat the region as a type 2 region, you're going to need, you know, hold on, it's region D. If you treat the region D as a type 2 region, because the bottom function, or I'm sorry, I want to say it's the right way. The function on the left is always going to be x equals 0. That's this function right here on the left. But the function on the right changes. It changes from this function, okay, which it would be, well, y equals a half x. That means x equals 2y. It changes from that function to this function. And that function would be, well, y equals 1 minus a half x. That's equivalent to x equals 2 minus 2y. So because of that, if you're going to treat the region D as a type 2 region, you're going to need to add two double integrals to get the volume. The first double integral is going to correspond to the lower half of region D. And the second integral is going to correspond to the upper half of region D. Okay. Are there any questions so far? All right. Well, where do you want to compute the volume by treating the region D? I mean, what's your preference? Do you want to treat the region D as a type 1 region, or do you want to treat the region D as a type 2 region? What's your preference? And I don't think this is a hard question, but all right. And Ryan, why are you saying type 1? I think it's obvious, but if you could, well, it's cleaner and would it be less work? Definitely, definitely. So in these problems, you always have to be careful in how you do your integration. Okay, you want to be careful. All right, so we're going to treat region D as a type 1 region. Now what I want to do is I want to compute, no, wait, hold on. I want to compute this volume here. May I go to the next page? Are we ready to go to the next page? Okay. Okay. So you can imagine, you know, a single integral takes work to compute. So a double integral is going to take more work. Okay. And when we get to triple integrals, it'll be even a little more work. Okay. But we need them all. All right. So let's compute this double integral. I go to the next page, and what I do, of course, is I iterate the integral by putting in my little grouping symbols. These grouping symbols here help me because it allows me to concentrate. Okay, I'm computing two single integrals. Okay, the first single integral is with respect to y. That's the inner integral. When I integrate with respect to the variable y, what variable gets held constant? The x. That's right, Robin. And so the antiderivative of 2 minus x minus 2y would be 2y minus xy minus y squared. I treat the x like a constant. And then I'm going to substitute in my top and bottom limits, which are functions of x. And I do that right here. Let me give you a moment to catch up. Please let me know if you have any questions. Okay, so, here we go. This is now just, doing computation. All right, and at some point here, we'll use MATLAB to help us, particularly with triple integrals. But I don't want you to use um, MATLAB yet to help you compute the double integrals, because you need to practice it, and you know the next exam, which is actually next week, next Thursday, it's coming up. I'm going to want to see work for these, for for the integrals. So that way you're showing me you understand the concepts. But all right, well, let's continue. So this is now a matter of just, I got to, take these binomials and square them. 1 minus a half x quantity squared would be 1 minus 1x plus a fourth x squared. And let me see here. Well, a half x squared is just a fourth x squared. And then what I do is I just, 2 minus 1, 2 minus a half x, that's 2 minus x, and then minus x times 1, and minus x times negative a half, that's just negative x plus a half x squared, and so forth, I got my minus here. You just have to be careful, but this is what you're going to get. And oddly enough, we have some simplifying out. We have the x, these two x terms cancel out, and the negative 1/4 x squared terms cancel out. And if I combine the rest of the terms, like terms, this is what I'm going to get. The integral, the volume will be the integral from 0 to 1 of 1 minus 2x plus x squared with respect to x. And now it's a calculus 1 problem. And remember, you're finding the exact volume here. You're not adding up volumes of bricks and approximating a volume. You're going to get the exact volume. Okay. If you have a tank, let's say you have a tank that's in the shape of this tetrahedron. Well, you want to know exactly how much water that tank can hold, because that's going to maybe be the water pressure, the water on the sides. It's going to determine how you're going to build the tank, or what are you going to, how strong are you going to make the sides, and so forth. I mean, we really need to try to get exact volumes. Okay, may I move to the next page? Are there any questions? Okay, John's feeling good. All right, let's go to the next page then. Okay, turns out that my volume is going to equal 1/3. Think of all the math that you used in this problem, all the knowledge that you've learned in your math classes in the past. Even algebra, right? All of it's being applied here. You can never hide from math, right? From your math skills. They always come up at some point, right? All right, are there any questions at all? How many think this is a pretty cool application of double integrals? Okay, Ryan's liking it. Thank you, Ryan. Thank you, John. Thank you, Robin. Thank you, Ryan. Thank you, Eric. Thank you, Jamal. All right, and we're going to relate these double integrals later on to concepts that you'll see in physics. All right, but we have to wait. Well, actually, we're going to see some applications in section 12.5. Like, for instance, moments about X and Y axes. Okay, how many have dealt with moments in their class, maybe another class, physics class? Okay, Christopher's familiar, and John. Okay, so all right. Well, let's get to the next example then, if we're good on this. Okay, this problem. Wow. All I want to do is evaluate this double integral. Let me give you a moment to copy it down. Okay, so let's see here. Now, we know that we can, again, I like to iterate the integral. Okay, I like to iterate the integral. And okay, well, we're ready now to integrate the integral from x to 1 of the sine of y squared dy. Okay, so what do you think? Can we integrate the sine of the angle y squared? Is there an antiderivative to the sine of y squared? Oh, okay. Robin doesn't think so. I don't think so either. You'd probably get a Fields Medal if you could find an antiderivative of the sine of y squared. Okay. Well, Robin's making a suggestion. Yeah. Okay. Try letting u equal y squared. If you let u equal y squared, then du will be equal to 2y dy. And so, sure, I mean, the sine of y squared is taken care of, but you have what's left is just a dy. I don't have a 2y dy, So good try, Robin, but I don't think that's going to work. But I appreciate appreciate your try there. Robin was going for that Fields medal, right? All right. So, well, what are we going to do? What are we going to do here? Well, notice that we're integrating here with respect to y first and x second. What if we were to try integrating with respect to x first and y second? So what if we were to try to do that? What if we were to use this order of integration? That might work. That might work. Could we just do this? Now let me actually hold on. Maybe I'll use my stylus on this. Don't copy this down. Don't copy this down. Okay, so are these two integrals equal to each other, you think? I mean, if you think back in section 12.2, if it wasn't like when you, like what, I mean, well, what did I do here? I just changed the order of integration and switched the limits. And like in section 12.2, when all of your limits were like, when all of them were constants, that would be okay. When all of your limits, you know, were constants, that would be okay. You could just switch, if you change the order of integration, you just switch the limits appropriately. But can we do that here? Why? Okay, that's right, Ryan. You have a variable here. X is a variable. Good. So you're not going to be able to do that here. Not going to be able to do that. So what we have to do is then, well, I mean, if I have an integral and I mean, I'm integrating with respect to y first and x second, I ought to be able to write an integral where I integrate with respect to x first and y second. But what I have to do is I have to, based on these limits here, I have to figure out what my region D is. Because what I'm really doing, right, is I'm using a type 1 region here because we're doing dy dx, and I wanna change it. I mean, the region won't change, but I want to do a type 2 integral instead. But to do that, I got to see the region, and so that's what we do. We're going to try to reverse the order of integration. Okay, we're going to try to reverse the order of integration and see if that helps. And based on the y limits here, okay, well, y equals x and y equals 1. Those are the bottom and top bounding functions of the region D. And then the x limits here go from 0 to 1. And so, you know, 0 to 1 on the x's. And so that you got a triangle. That's what your region D looks like. It looks like a triangle. It has to be. It has to be that. Has to be a triangle. But what I want to do now is, instead of doing dy dx, I want to do dx dy. And so I'm going to treat that triangle as a type 2 region. Let me give you a moment to copy down to here. Okay, and let me know if you have any questions. All right, so, well, of course, since we're going to explore doing dx dy using that order of integration, that means then that the x limits are going to be functions, well, functions of y. So you're bounded here on the left side by the line x equals 0. So that's your bottom limit in the inner integral here. And then you're bounded on the right side by the line y equals x. But of course, I write that as x equals y. Okay, and then the y limits are going to go from 0 to 1. All right, and now we're going to see if dx dy is going to be the way to go here. Well, if it isn't, then we're out of luck, Okay, may I move to the next page? All right. Okay. Thank you. Okay, so we're doing dx dy. Doing dx dy. And of course, for the inner integral now, and you see I always use, how many find the grouping symbols helpful? How many use those? The grouping symbols in their work? Okay, good, Ryan, good. Good, Christopher, good, John, excellent. They are really helpful. Wait till you get to triple integrals, you know. Well, okay, so the inner integral, we're integrating with respect to x. So what variables held constant when we integrate with respect to x? What variables held constant? The y. Good. So that means, that's right, Ryan. So that means the sine of y squared is like a big constant. I'm treating it like a big constant. So the antiderivative of the sine of y squared is just the sine of y squared times x. So I was able to take the antiderivative. Now I substitute in y and 0. Okay, and I end up with this integral here. And we're at now it's a calculus 1 problem. So now, Robin, I'm ready. We're ready for that substitution. We're ready for a substitution here. We're going to let u equal y squared. Then du is 2y dy, so y dy is a half du. Of course, your limits become 1 squared and 0 squared. You always have to change your limits. Turns out they're going to be the same, but all right, let me give you a moment to catch up. Please ask any questions. Christopher, this is both of these. Yeah, this is absolutely representative of what you could see on the test. But both questions are representative, and I realize they take some time to do. It sounds like the last exam, looking at the times, people took, normally between 2 hours and 2.5 hours, but I gave 3 hours. But I always keep in mind it takes time to do problems. But of course, you have to be ready to take the test. So you have to practice and do your homework so you're as ready as you can be. But I do, once you do a few of these kind of problems, you're going to get very good at this, like this second problem in terms of reversing the limits. You'll get very, very comfortable with that. But you have to draw the region. You can't. Sometimes students let me go to the next page here. So now we're continuing here, and the final answer for the integral is going to be 1/2 times 1 minus cosine of 1. And that's what Webassign would want. It does not want a decimal. Okay, decimals are, when you can compute integrals and get exact answers, which the ones you're going to get you'll be told in the homework or on an exam if you need to approximate the integral. If you can get the exact answer, that's what Webassign wants, and that's what I want. And yeah, you'll get comfortable with this material, but you have to practice it. You can't turn your back on it, and you can't wait till the last minute to work on it. It takes time to absorb. Time to absorb. I mean, some I mean, there are well, yeah, just takes time to absorb. Well, Jamal, it sometimes Webassign might do that. I mean, traditionally, when I've looked at it, just from what I've other students, I had a student who put in a decimal answer on a problem, and the WebAssign didn't take it. And he asked why I won't take it. I said, because you can get the exact answer. It doesn't want a decimal. Getting an exact answer simplified radical form, it means that you need to go, you can't use a computer to get the answer, really. You got to work, well, you know what I mean. You can't, they want you to work it out, so you can show that you understand the concepts. But I'm nothing's perfect. Nothing's perfect. But all right, very good. Are there any other good questions? All right, let me stop the recording then.